Bismillah ar-Rahman ar-Rahim. I will talk today about the nerve stimulator. Nerve stimulator devices has been very advanced in recent years. So here in this presentation, I will talk about only the basics. So let's begin. The agenda of this presentation is first I will present a brief introduction. Then I will talk about how does the neurostimulator work. The neurostimulator is the core of the nerve stimulator device, and then I will conclude by presenting the operation of the nerve stimulator. First, what is a nerve stimulator? Nerve stimulator is a device used to send electrical signals to any parts of the nervous system, usually to treat neurological problems or inhibit pain. So all organisms, cells have voltage potential, also called membrane potentials, measured from the outside to the inside. It usually ranges from minus 60 to minus 100 millivolts. For muscles and nerve cells, it is typically around minus 90 volts. Only nerve and muscle cells can generate action potentials. It is also known as spikes, which are electrical pulses that propagate across their membranes. These cells are the only cells type that can produce these uniform cells. Action potential resulted from the decrease in potential difference. This decrease is called depolarization when it reaches a certain threshold. An insulating layer of Schwann cells wraps around the nerve fibers to form myelination. Nerve fibers come in a variety of shapes and sizes. The diameter and degree of myelination of each fiber type can be identified anatomically. These properties heavily influence the electrophysiologic behavior of distinct nerve fibers, such as the speed with which action potentials propagate and the excitability threshold. Motor fibers, for example, A alpha and A beta, and pain fibers are the most common distinguishing traits. As you can see in this picture, the nerve fibers of A alpha and A beta, etc., has a myelin sheath. This myelin sheath affect the electrophysiologic behavior and the impulse propagation, whereas the C fibers, which is the pain fibers, doesn't have a myelin sheath. Now, how the neurostimulator circuit work? As I said before, neurostimulator is the core of a nerve stimulator device. This is a very basic block diagram of the neurostimulator. Keep in mind that there are many other designs. Some of them are very advanced, which is we are not interested in them here. So for this block diagram, the load represents the electrode skin interface resistive and reactive components, as well as the bulk tissue resistance. Pulse repetition rates range from 1 to 10 times per second. T1 is a line transformer that converts 60 Hz main powers to 30 volt AC power after passing via 4-diode bridge and a bulk capacitor filter. The rectified voltage is sent into a regulator circuit whose output may be adjusted between 0 and 12 volts and sets the supply voltage to the stable. Because the primary of the elevator transformer T2 loads such a circuit, the oscillation across the secondary reaches large voltage amplitudes and provides the compliance voltage required to provide the desired stimulation current. The peak amplitude at the secondary of T2 fluctuates from 0 to 220 volts as a function of the regulated voltage. A high voltage supply is provided to switching voltage to current converter built on a cascade current mirrors, which sends a constant amplitude pulsed current to the load after a second full bridge rectifier. Now let's talk in short about the operation of the nerve stimulator. The initial amplitude for nerve stimulation is determined by local practice and the projected skin nerve depth. In most cases, an amplitude of 1 milliampere is chosen to begin with for superficial nerves. For deeper nerves, the initial current amplitude may need to be increased between 1.5 and 3 milliampere until a motor response is provoked at a safe distance from the nerve. Once the desired muscle response has been obtained, the current intensity amplitude is gradually reduced and the needle is gradually advanced further. The needle is advanced and the current is reduced until the desired motor response is obtained with a current of 0.2 to 0.5 milliampere and a stimulus duration of 0.1 millisecond. If the motor twitch is lost during needle advancement, the stimulus intensity should be increased, first to reestablish the muscle twitch before moving the needle blindly. Once the needle is properly positioned close enough to the nerve at around 0.3 milliampere current amplitude and 0.1 millisecond pulse duration, 1 to 2 milliliter of local anesthetic is injected as a test dose using low opening injection pressure to eliminate muscle twitch. The needle should not be advanced too quickly as this increases the risk of injury. Furthermore, the best needle position for producing a good near threshold motor response may be overlooked. That is for this presentation. Thank you for listening. If you have any comment or question, please feel free to leave it in the comments. Thank you very much.